Welcome to this episode, where we're diving into the captivating world of concurrent programming and distributed systems. Today, we're going to unpack the concept of linearizability and explore what it means for system design. We'll also compare it with other consistency models, including sequential and causal consistency. By the end of our discussion, you'll have a clearer picture of how these models shape the behavior of distributed systems and the trade-offs that come with implementing them. Let's start with linearizability. This consistency model is all about making operations in a distributed system appear to happen instantaneously at a specific moment in time. It maintains a strict order that's rooted in real-time constraints. So if one operation finishes before another starts, the system reflects that sequence. This property is especially crucial for applications that demand a high level of consistency, like banking systems or online transaction processing. However, achieving linearizability isn't without its challenges. The synchronization overhead required to keep this strict order can be quite significant, which is why many systems choose to forego it in favor of more flexible models. As we explore the practicalities of implementing linearizability, we'll highlight techniques like compare and swap operations and consensus mechanisms that help in this endeavor. One particularly effective framework is the reusable infrastructure for linearizability, or RIFL, which shines in the context of remote procedure calls. Now, let's shift gears and talk about sequential consistency. This is another important model in the distributed systems landscape. While both linearizability and sequential consistency aim to provide a consistent view of operations, their approaches differ quite a bit. Sequential consistency allows for more flexibility by letting operations be observed in different orders across processes. As long as each individual process sees its own operations in the correct sequence, this flexibility can sometimes lead to what we call stale reads, where a process might access outdated information due to the absence of global synchronization. Sequential consistency can be advantageous in scenarios where performance takes precedence over strict ordering, but it also introduces complexities that developers need to navigate carefully. As we dig deeper into consistency models, we come to causal consistency, which takes a different approach altogether. Instead of relying on physical clocks, this model establishes a logical order of operations. In causal consistency, causally related operations are observed in the same order across processes, which helps to prevent inconsistencies that could stem from divergent operational histories. To illustrate this, think about an online forum conversation. Imagine a thread where users are responding to each other. If one user replies to another's comment, the sequence of those responses needs to reflect that relationship to maintain coherence. Causal consistency ensures that all participants in the conversation agree on the order of interactions, which is vital for a smooth user experience. Speaking of user experience, causal consistency also brings session guarantees that enhance how users interact with applications. Even when users are connecting to different servers, they can still expect a consistent view of the database. Some key guarantees include monotonic reads and writes, which means that once a user reads a value, any subsequent reads will return the same or a more recent value. Plus, users can read their own writes, ensuring their contributions are immediately visible. Achieving these guarantees involves using logical clocks and metadata to track the order of operations. By processing updates only when all preceding actions have been applied, causal consistency prevents confusion and maintains a seamless user experience. Messages that arrive out of order are held back until the necessary context is established, so users don't encounter inconsistencies in their interactions. As we wrap up our exploration of these consistency models, it's crucial to recognize the trade-offs involved. Linearizability offers the highest level of consistency, but it comes at the cost of performance due to synchronization overhead. Sequential consistency provides more flexibility, but can lead to stale reads. Causal consistency finds a middle ground, offering a logical order of operations while still ensuring a coherent user experience. When designing robust concurrent systems, understanding these nuances is vital. Developers must evaluate their application's specific requirements and choose the right consistency model based on the desired balance between performance and consistency. In conclusion, our journey through linearizability, sequential consistency, and causal consistency has shed light on the complexities of maintaining order and coherence in distributed systems. Each model presents its own unique challenges and benefits, and the choice of which to implement can significantly influence system performance and user experience. As technology continues to evolve, having a nuanced understanding of these concepts will be essential for developers and engineers looking to build reliable and efficient concurrent systems. Thanks for joining us in this episode, and we hope you've gained valuable insights into the world of consistency models in distributed systems.